Welcome back. Today I'll be talking about some consequences of the axioms. So last time we discussed about axioms for probability, uniform probability laws. Now today we'll talk about consequences of those axioms. The first thing we'll talk about is for probability, that is probability of event A is greater than or equal to 0. That was the axiom we talked about last time. And counterpart of that is probabilities are also less than or equal to 1. So we'll talk about that today. So that is probability of A is equal or less than 1. Last time we talked about probability of sample space equal to 1, and consequence of that is probability of empty set is equal to 0. And thirdly, for disjoint events, probability of A union B is equal to A, probability of A plus probability of B. And counterpart of that is and counterpart for that is probability of A plus probability of complement of A equal to 1, and also will expand on the A union B. We will say that probability of three events where A union B plus C is equal to probability of A plus probability of B plus probability of C. So what we do is we generalize additive axiom, which was generally for two disjoint events, but now it will be for more than two events. So let me just write it down a little bit more better way. Uh, probability of A plus probability of A complement is equal to 1, and this will be probability of A union B union C is equal to probability of A plus probability of B plus probability of C. And in the end, we'll also talk about the general application of these axioms, that is probability of set S1, S2, Sk is equal to probability of individual elements S1, which is equal to probability of S1 probability S2. So that's what we're gonna prove out today. So let's start with the for our purpose of referring these axioms, let's refer to those as A, B, and C. So let's have a sample space. So let's have a sample space So let's have a sample space where we have A and A complement as a subset of that sample space, and they are disjoint. We know that from a second axiom, probability of entire sample space is equal to 1. And this sample space is equal to A union of A and A complement. Since these events are disjoint, this means we can apply additive axiom and write the probability as a sum of probability of event A with the probability of complement of A. That means we can write this as probability of A plus probability of A complement A complement, which is equal to probability of A union A, which is equal to 1. This will equal to let me just make I think I made a mess here. Let me just make it a little bit better. We know that from B, we know that probability of sample space is equal to 1. And we also told that it's given that sample space is equal to union of A and A complement. So we can substitute the sample space with A union A complement which is equal to 1. Now we using the additive theorem from C, we can say that probability of A plus probability of A equal to 1, or probability of A equal to A probability of A intersection C. So we know that now at this point we can say that this is always greater than equal to 0 from A. That means positivity, right? This is always non-negative. So what? So if this is the case, then this will be always equal or less than 1. Therefore, probability of A is equal or less than 1. So we prove this out. Now let's move on to second axiom, second consequence axiom. It says that probability of empty set is equal to 0. For this one, let us note that probability of 1 is 1 is the probability of the set plus probability of the complement of the set. And let us use this property for case where set of interest is entire sample space. Now the probability of entire sample space is itself equal to 1. So what we know is that for this one, to prove this one, we need to do is probability of 1 is probability of entire sample space plus complement of the sample space. We can say that, right? Now we know that probability of sample space is equal to 1 plus probability of sample space. Therefore, we can say the probability of complement of sample space equal to 0. Complement sample, and we know that complement sample space defines all the possibilities. So there's a complement sample space is always null or empty state. So that's how we prove this out. And thirdly, let's take the let's general let's no let me see. Let's generalize. Let's generalize the disjoint event. We know that so we have our sample space with 3 events which are disjoint. A, B, and C. And we are interested in probability of union of A, B, and C. We have additive axiom in our hand. We form one set by taking the union of A and B. Let's take the one set by taking union of A and B. A union B becomes one set, and C as another set. And probability of this is equal to probability of A union B plus probability of C. So this can be thought as a union of two sets. A union B is one set and C as a second set. Now we have used the additivity theorem or axiom to write as probability A union B plus probability of C. Now let's break down the probability A union B into more granular terms. So for this, we need to break this further by probability of A plus probability of B plus probability of C. Okay, so this now we have proof for three disjoint events. We can, by induction, we can do this for up to k events. So this is a generalization of case where we are dealing with union of finite many disjoint events. One the application of this expression is that it is very useful for calculating the probability of finite set. Let's say we have a sample space, and within sample space we have different events, and which are, let's say, finite. Let's say up to k events, 1 through k events. These elements, these events or elements are finite and distinct. They are not same, and they are finite. They are not infinite. We can, what we can say about the probability of this finite set is that we can think of these elements as a individual sets of one element. So these all elements are, you can assume them as a set of one element, which are all disjoint. Using additive property for union of k disjoint sets, we can write this as a sum of the probabilities of different single element sets. But intuitively, we can also talk just about probability of particular element and use simpler notation. So when using simpler notation, we'll be talking about probabilities of individual elements. Although, in terms of formal mathematics, what we can really mean is probability of the set that comprise one of particular element S1 and so on. To summarize, today we proved out that probability of A is less or equal to 1. Secondly, probability of null set is equal to 0. And thirdly, we generalize the expression for disjoint event up to 3 event, and which can eventually be proved out for up to k elements. And also we apply the different axioms to prove out that probability of finite set of elements is equal to individual probability of individual elements. Thank you.